In a previous video linked below, we looked at phase equilibrium. In the current video, we're going to add an extra level of complexity by looking at what is called multi-component phase equilibrium. Multi-component essentially meaning solutions, where a solution is a homogeneous mixture, and in this video, the component A will be called the solvent, and component B is the solute. As seen with the single component equilibrium, the chemical potential is what drives the equilibrium either forward or backwards. As a reminder, the chemical potential is how the Gibbs free energy changes with the number of moles of any given component. Putting it another way, the Gibbs free energy is simply the sum of all the chemical components of any of the given components of the system. Since the potentials related to the free energy, the chemical potential of A is equal to minus S dt of A plus V dP of A. In a multi-component system, there's an extra level of complexity. You have mu star, which would be the chemical potential of the pure solvent. You also have a different state, mu zero, which is the chemical potential of the solvent in the standard state, where once again the standard state means that everything is at 20 degrees C, all gases are at 1 atmosphere, and all solutions are at 1 molar concentration. Finally, you have the chemical potential of the solvent in the mixture. For a mixture, in order for a mixture to be in equilibrium, the potential of the solvent in the mixture has to be equal to the potential of the pure solvent plus VdP, or RT log P of A in the mixture divided by P of A in the pure solvent. From Raoult's law, this becomes RT log the mole fraction of A in the mixture. This can be rewritten that the log of the mole fraction of the solvent in the mixture is equal to the potential of the solvent minus the potential of the pure solvent over RT. Since the chemical potential is related to the Gibbs free energy, this is essentially equal to the Gibbs free energy of vaporization over RT. So essentially, the amount of solvent you have is related to the heat of vaporization of that solvent. Now, for a solution where I have a non-volatile solute, I can rewrite how does the change in temperature change the behavior of the solution. Mathematically, that means how does the log of the mole fraction of solvent change with temperature versus 1 over R delta G over T change with temperature. From the video on Maxwell's relations, the change in G with respect to T is equal to minus the entropy. Entropy is equal to dQp over T, since the temperature is changing the pressure solvent, or in other words, delta H of the transition. So this simplifies to log of the mole fraction of solvent is equal to minus the heat of vaporization of the solvent over R times the integral 1 over T1 minus 1 over T2. This will eventually wind up looking a lot like general chemistry. This can be simplified in a couple of ways. First of all, we are talking about very dilute solutions where the mole fraction of solvent is very close to 1. So using Stirling's approximation, as the mole fraction of solvent approaches 1, the log of 1 approaches 0. So to an approximation, the log of the mole fraction of solvent becomes a very small number, winds up being equivalent to the mole fraction of the solute, which is a small number. So I get the mole fraction of solute is equal to the heat of vaporization of the solvent over R, 1 over T1 minus 1 over T2. Again, all of this coming from the second law of thermodynamics. This will look familiar from general chemistry in a second. I can simplify. 1 over T1 minus 1 over T2 is the same as delta T over T1 squared, where in this case, T1 is the phase transition temperature of the pure solvent. So the mole fraction of solute is delta H of the solvent over R times the change in temperature over the phase transition temperature squared. By definition, the mole fraction is the moles of solute over the moles of solvent plus solute. Again, this can be approximated since it's a dilute solution. There's very little solute in it, so the mole fraction of the solute can be approximated as the moles of solute over the moles of solvent. I'm going to divide this whole thing by the molecular weight of the solvents. Why am I doing this? I wind up with the following. Moles of B over moles of A winds up being moles of B over the moles of A times the mass of A, or moles of B over kilograms of A, is equal to delta H divided by R times the mass of A times the transition temperature squared times delta T. I rearrange this slightly. Delta T is R times the mass of A times the transition temperature of A over delta H. Moles of B over kilograms of A is the molality. All of the terms, the gas constant, the molecular weight of A, the normal transition temperature of A, and the phase transition enthalpy of A are all constants for whatever that solvent is. So I get delta T is equal to some constant, which depends upon the solvent, related to the molality. One might remember this from freshman chemistry. Once again, that constant is equal to R times the mass of A T squared over delta H. There are two common phase transitions. The first common phase transition is freezing. So I get the freezing point constant for any given solvent, where it's R times the mass of that solvent times the freezing point squared over the heat of fusion. Furthermore, since delta H is a state function, it will change sign when it changes direction. Freezing, or any phase transition, is an equilibrium. So if I want to melt ice, I'd have to add energy. But since I'm defining this as freezing water, I've defined delta H of fusion as being negative. Therefore, Kf is negative, and the freezing point depresses. So if my solvent is pure water, normally water remains a liquid to 0 degrees, where it turns into a solid. A water solution will stay liquid to below 0 before it turns solid. The other common phase transition is boiling. In this case, delta H is replaced with the heat of vaporization of a given solvent, and you have the boiling point constant for that solvent. Since I am talking about boiling, the heat of vaporization will be positive in that direction, so boiling point increases. So again, with my water, pure water will boil at 100 before it turns to gas. A solution of water will boil at greater than 100 before it turns into gas. So what can be seen thermodynamically from the chemical potential? Nothing happens unless it reaches a lower energy. Solutions are more stable than either component, the solvent or the solute by themselves. And you can see this quite clearly here, where pure water only stays liquid between 0 and 100 degrees C, while any given solution will remain liquid over a wider range of temperature and is stabilized. For the same situation of a non-volatile solute, how would pressure affect equilibrium? When the solution is stable, the chemical potential of the pure solvent is equal to the chemical potential in the mixture. In the mixture, that's equal to RT log of the fraction of the solvent at some different pressure, P plus pi. I can rearrange this as the potential at T and P minus the potential at T and some higher pressure, which is equal to VdP, since I have an isothermal system now, of RT log chi A. So, V with a squiggle over it is the molar volume. The volume of 1 mole of a given solvent is equal times the change in pressure is equal to RT times the log of the mole fraction of solvent. Again, with Stirling's approximation, that's RT times the fraction of solute. The change in pressure is pi. I've gone from P plus pi to P. Is going to be equal to RT times the log times the moles of B over the moles of A. So pi is equal to the moles of B over the molar volume of A times the moles of A RT. In other words, you have the osmotic pressure relationship, where the osmotic pressure of a solution is equal to the molarity, moles of B per liter of A, times RT. So osmotic pressure, also learned in general chemistry, is once again the consequence of the second law. So far, we've been talking about ideal solutions, where there are minimum interactions between molecules. This is rarely the case. For non-ideal solutions, you have salvation effects and electrostatic effect. The solute dissolves because it attracts solvent molecules. This lowers the amount of solvent in the solution and creates a bulkier component of a mixture of solvent and solute. There are also electrostatic effects between polar and nonpolar, or polar and polar solvents, that lead to attractions and repulsions that lead to non-ideality. So for a non-ideality, instead of concentration, one talks about activity, where the activity of any component I is going to be equal to gamma, the activity coefficient, times whatever the concentration of I is. The activity coefficient is a measure of the relationship between the solvent and the solute. It will change for any given combination of the same solvent with different solutes, or the same solute with different solvents. If I have a perfectly ideal solution, the activity coefficient, by definition of 1, is 1. This leads to a minor change in the colligative properties. Raoult's law. Instead of being the pressure of A is chi A times the P star of A, chi is replaced by the activity, but the activity is simply equal to the activity coefficient times the mole fraction. Basically, you're multiplying Raoult's law by gamma. The same shows for phase changes. Delta T is some constant times the activity, where the constant, as shown, is R times the mass of the solvent, freezing point or boiling point of the solvent, or delta H. This is the normal. Delta T is equal to K times M, where the activity is the mole fraction of solvent times the molality. And finally, also osmotic pressure. Instead of being equal to the molarity times RT, it's equal to the activity times RT, which is equal to the activity coefficient times the molarity times RT. So that's essentially the thermodynamics of solutions, wherein you wind up with the same conclusions that you had previously learned in general chemistry, the colligative properties, phase change, osmotic pressure, how a solution behaves differently from a pure solvent. In the following video, linked also below, we will examine how thermodynamics affects and influences reaction equilibrium. Thank you very much for listening, and I hope you enjoyed this and found it useful.